So, welcome back. Now, what we are going to start today is about the non-invasive velocity measurement techniques. So, till now we have already discussed about the invasive measurement technique, and in invasive measurement we have discussed about the pitot tube, we have discussed about the hot wire anemometer, we have discussed about the optical fiber probes, and whatever we have tried to learn that though some of the technique like optical fiber probe and hot wire anemometry, you reduce the size of the probe, but the invasive nature is still be there. And because of that, the measurement can change, or the flow dynamics it can change at the point of measurement itself. And therefore, there is a need, if you want a better accuracy, there is a need to develop a non-invasive technique. Further, that as we have discussed that in hot wire anemometer as well as in optical fiber probes, that the probe which you are inserting inside cannot sustain a medium which is very corrosive, or kind of say the medium conditions are very harsh, say very high pressure, very high temperature, then the life of the probe will reduce, and that will actually enhance the price of your measurement. And therefore, the non-destructive technique or non-invasive technique has been used, which does not actually interfere with the flow, and so therefore, you can use these techniques in a very adverse environment, say very corrosive flow, a very high temperature flow, a flow which is highly contaminated. Okay. So, all these flow where the scaling can be there. So, all these flows you can use this non-invasive measurement technique, and that gives the major boost to the measurement technique as per se, that you can do the measurement without disturbing the flow, and that too for a very harsh flow conditions. So, that is the major advantage of non-invasive technique. And as I said that there are several class of the non-invasive technique, there are different non-invasive techniques available to measure the velocity. We are going to discuss in this part some of them, and those are mainly laser Doppler anemometry, it is also called velocimetry, or we will call in LDA. We will discuss about the particle image velocimetry, we call it PIV. Then we will discuss about magnetic resonance imaging, that is called MRI. Then we will also discuss positron emission particle tracking, we call it PEPT. We will discuss about radioactive particle tracking, called it RPT, and we will say that X-ray XPTV, X-ray particle tracking velocimetry. So, XPX. So, all these techniques we will try to discuss. X-ray particle tracking velocimetry, that is why XPTV, we will discuss about all. Now, the major advantage of all these techniques is that they can be used, they do not disturb the flow, they can be used for the harsh flow conditions. Harsh flow conditions, so I am talking about the chemical property of this flow, say if very highly acidic medium is there, highly corrosive medium is there, highly contaminating medium is there, you can still use these flows, but each have their own limitation, their own advantage, their own working principle, and that is what we are going to see here now. So, what we will do, we will first start with a very basic technique, or kind of one of the initially developed non-invasive technique, a very old non-invasive technique, that is laser Doppler anemometry. So, we will let us try to understand that what is laser Doppler anemometry. Now, definitely one term which all of you might be have heard, definitely, that is called Doppler. So, you might have heard about the Doppler effect in your undergraduate courses and even in your +2 level courses. We will try to revise some of the fundamentals and how the Doppler effects is actually being used to measure the velocity. So, what we are going to do in the laser Doppler anemometry, we are going to use the Doppler effect to measure the velocity field. Now, how we are using it, what is Doppler effect, we will all kind of try to understand all this. So, as I said, what is laser Doppler anemometry? Laser Doppler anemometry is a measurement technique that is used to measure the fluid velocity by detecting frequency shift of a laser light that has been scattered by small particles moving with the fluid. So, that this technique actually uses the scattering of the because of the lights moving particles, and that is the reason that why the Doppler effect comes into the picture. So, it means what, if suppose we have a light system where we are incidenting the light at a certain place without kind of scattering it, without having any particle inside in a certain medium, then we will receive some signal on our detector. Suppose if I am using a receiver, I am incidenting a laser light or light on a particular medium, I will receive some of the signal. Now, if I will flood that medium, or if I will introduce some neutrally buoyant particles which are moving at a certain velocity in that medium, then what will happen, these particles will scatter the lights, and now the signal received on the receiver will be less or higher than the signal received initially without the particle presence. So, what we can do, we can correlate the shift in the signal, okay, by velocity of the fluid, because we have introduced some of the neutrally buoyant particles. It means they are going to follow the path of the particles, path of the fluid. So, we can calculate the shift in the frequency with the velocity of this moving object or moving particle, and that is the basic principle of laser Doppler anemometry. Now, the light which has been incidented on this, or the waves which has been incidented in the medium, is a laser source, and that is why we call it as a laser Doppler anemometry. Okay. So, we are going to do the Doppler shift, and what we do a very simple thing. Say we have a laser light source. So, this is laser source. We are incidenting a laser, say this is the laser, and let us assume that we are breaking the laser in these two parts. We are incidenting it on a particular zone by using a lens, and this is say my measurement volume or measure the flow area where we are measuring, and then again we are collecting the signal and focusing it on a detector. Say this is my detector or receiver. Okay. So, what will happen, suppose there is a fluid which is flowing inside, okay. This is fluid which is flowing inside. Once this laser light will fall, what will happen, this detector or receiver will receive certain intensities. Okay. Now, that intensity, how much it will receive, that will depend on the intensity of or frequency of this laser light and medium density. Okay. So, that we know already. So, we will come to detailed mathematics later on. So, that it will receive some of the signal. Okay. Now, if I introduce some of the neutrally buoyant particle in it, then what will happen, this particle once they will go, it will actually do some frequency change. Now, they will scatter the light. Now, once they will scatter the light, they will scatter it in all the direction, okay, and some of the scattering will also fall in this direction, in the direction where the receiver is there. So, what will happen, say initially the frequency was something, now you will get the frequency which is scattered also, this frequency, and there will be a shift in the frequency. Now, the receiver will see that the frequency has increased, okay, or frequency has decreased, that will depend on the velocity of the object, okay, velocity of this particle and the direction of this particle velocity. So, this shift in the frequency, this additional shift in the frequency is directly correlated to the velocity of the moving object, and that correlation can be established by using the Doppler effect, and that is why the Doppler effect actually is being used to measure the velocity of the flow fluid or flowing fluid in the LDA. So, that is the whole principle of the LDA. Now, we will discuss about the Doppler shift and other mathematics of the reconstruction in detail and the equipment used, but that the basic principle is you are actually introducing some seed particles, we call it seed particles, which are nothing but a neutrally buoyant particle. So, these are seed particles, and these seed particles are nothing but the marker of the phase which velocity you want to track. And these particles are neutrally buoyant. It means the density of this seed particle Sp is equal to the density of the fluid. So, they are neutrally buoyant. So, they will follow the path of the fluid. Okay. So, the velocity of this neutrally buoyant seed particles can be correlated, or can be said that if the particles are very, very small, they are following the path of the fluid, their velocity and the fluid velocity will be equal, and the velocity of these particles can be directly correlated with the Doppler shift in the frequency observed at a receiver. Okay. So, that is the basic principle of the laser Doppler anemometry. So, now what we do in the Doppler shift, or how it happens. So, let us assume that a wave is being incidented. Okay. Now, this can be a wave, this can be a light, this can be ultrasound waves, anything, or radio waves, anything, all will follow the Doppler shift. Okay. So, what we are doing? We are using the laser light. Why the laser light? They are monochromatic lights, their penetration lengths are better. So, the signal to noise ratio is much better in case of the laser compared to the ultrasound or radio waves, and that is the reason that the laser is being used to measure the velocity. Okay. But in principle, whatever the mathematics we will do, you can use the same mathematics for the radio waves, you can use the same mathematics for ultrasound waves. Okay. Or any sound wave. So, you can use the same mathematics here. So, what we are going to do? We are saying that suppose there is a wave which is being falling here at this place, okay, at a certain frequency and certain wavelength. So, say the wavelength of incidenting is lambda I and the frequency is f I. So, why I am using I? I means incidenting waves or incidenting light. Okay. Now, suppose there is a receiver which is being, there is some the particles are there, and because of that some scattering take place, and the receiver is actually on this side. So, say this is my receiver, okay, this is my receiver, okay, it is scattered. Once it is scattering, it will go in all the direction. Okay. So, this is some scattered light it is going on, and there is some velocity which is coming here. So, this is the velocity of the object. So, object which is moving in this direction, and this is the velocity v of the object. Okay. In this direction, the receiver is being scattered, and that is scattering actually the light or the wave which is being incidented on this particle, and that is going at it in this direction, okay, receiver direction. So, how the Doppler shift will work? So, we know that if suppose this is a light, then we know that the formula, the correlation between the f frequency and wavelength, and that is what? F into lambda is equal to c, where c is speed of light. Okay. So, it means you can say f is equal to nothing but c upon lambda. This you have already done. Okay. Just I am trying to revise it. So, this you have already done, that it will be f is equal to nothing but c upon lambda. Okay. That whatever the frequency will be there. Now, that is the frequency. Suppose I am talking about the incident waves, that will be incident light, it will be c upon lambda I. Okay. So, that part is clear. Now, what is there? This will be the incident which will be receiver will receive, okay, incident light frequency, which is the receiver will receive if there is no particle. Now, if suppose there is a particle which is moving with a velocity v, okay, the way we have defined the particle which is moving with a velocity v, then what will happen? How much of the intensity change, what will be the frequency now you will see, or the change in the frequency you will see on the receiver? That will depend that what is the velocity of the seed particle. So, we can write it that if suppose there is a particle, in presence of the particle, what will be the frequency which you will see on the receiver. So, that we can write it as f p, and f p is nothing but c minus v into upon lambda. Okay. Now, this can be minus, this can be plus. If it will be minus, if the velocity is in the direction of the velocity of the source where the it is incidented. It means if the velocity is in this direction, the direction at which the light has been incidented, this will be minus. If it is the opposite direction, then this will be the plus, and that is why I am introducing a unit vector I, which value is 1 if it is parallel to the incident direction, is minus 1 if it is opposite to the incident direction. Okay. So, once it is parallel, what will happen? You will see the waves which will become, so this is the say incident waves is coming it in this direction, you are moving it in this direction, then you will see the lesser frequency, the frequency will be reduced. Okay. So, suppose someone is blowing horn, someone is driving a motorcycle and he is blowing horn, okay, and if suppose you are also moving, okay, let us assume, and you are moving far from him, it means you both are moving in the same direction. So, you are moving far from him, then you will see the less frequency. Okay. So, what will happen, that the frequency will actually reduce. So, let us see this. So, let us assume that someone is blowing a horn and let us assume you are moving, source is not moving. So, this is source, this is you, okay, and you are moving it in this direction. If someone will blow horn, what will happen, you will see certain frequency in this way, you will see certain thing. Now, if you are moving far, what you will see, you will, this frequency will be reduced, okay, this will be shift, that will be more diversion will take place. So, this will be actually intensity of this frequency will reduce, and what you will see, will not see the original intensity which you are seeing if you are somewhere here. So, at this place you will see the lesser intensity. So, if you are moving at a velocity which is the similar direction to the velocity at which the waves are being introduced, you will see reduce in frequency, and that is why I see C minus V, okay, and the value of I in this case will be plus 1. But assume that you are moving in the opposite direction, then what will happen? Now, with the time you will see more intensity, the intensity of the sound will increase. So, the value of I, if you are moving opposite to the direction at which where the waves are being propagated, you will see the positive shift in the frequency, you will see the increase in the frequency, and that is why this value will be plus, and therefore, the value of I will be equal to minus 1. So, I hope this is clear that what you will see in case of this, okay, and this will be the lambda I. Okay. So, F I is the frequency of incidenting light, okay, the frequency of particle, this is being particle this frequency or the light which has been fall on the particle, lambda I is the wavelength of incidenting light. Okay. So, this is the way the Fp will be given. Now, what we need? We also need to find that what will be the lambda p. Lambda p means what will be the wavelength of the particle frequency. Okay. So, the light which has been transferred from the particle, what will be the frequency of that light? So, we can say that this lambda p, that is actually about the Doppler shift, that the lambda p is equal to C upon F of p. Okay. That will be the lambda p. So, it is same thing what I have written, F p is equal to C upon lambda p. So, lambda p is equal to C upon F p. Now, F p value we have already calculated, that is C minus V I upon lambda I. So, we can write it as C into lambda I upon C minus V into I. I is the unit vector. Okay. So, that is, this will be the lambda p. Okay. That will be the lambda p. Now, if I assume that the source is also moving, okay, if the source is also moving towards this, then what will happen? You will see a certain velocity again, and the frequency of the incident light where the source itself is moving will change, and let us assume that is nothing but lambda s. So, lambda s will be what? It will be equal to C upon F p, and this C will not be the velocity of the light, but it will be C minus velocity of the object in the direction of the source. So, say let us assume that that is j. Okay. So, if it is parallel to the source direction, it will be negative again. If it will be opposite, then it will be positive. Clear? So, now we have done that lambda s will be equal to what? C minus v of j upon f p. Okay. Now, f p we can replace again from the value which we have calculated. So, we can say that lambda s, sorry, f p is nothing but c minus v I upon lambda s. So, lambda s will be equal to lambda I c minus v into j upon, that is lambda, sorry, this is f p c minus into c minus v into I. Which I and j are the unit vectors. Okay. I and j are unit vectors which shows the direction. Vector which shows whether the scattered light is moving towards the receiver or it is moving far. Okay. So, that is what is the I and j are the unit these things. Now, what you have done, we have calculated the lambda s, the wavelength of the how that the source will be there. Okay. Now, what we are going to do, we are going to say that where the scattered light has moved, the wavelength of that scattered light we have already calculated. Okay. So, now what we can do, we can calculate the value of f s, and f s will be nothing but, it will be again c upon lambda s. So, f s will be nothing but c upon lambda s. Okay. And lambda s can be written as c upon, this will be c minus v into I upon c minus v into j. Okay. And that is multiplied by lambda I. So, that is the way f s will be given. So, f s we can write it in form of this, and this is f s, and earlier whatever we have said that whatever the lights which will be incidented here, that f p we have already calculated, and the incident of the light f I we have already calculated. Okay. So, f I we have already calculated, f p we have already calculated, and now we have calculated that the frequency of the scattered light, okay, the direction it is being scattered. So, this is the I direction, j direction, sorry, the scattered light. Okay. This is the I direction. Okay. So, we have already calculated that the scattered light frequency. Now, what we need to do, f d is nothing but this will be equal to f s minus f I. So, Doppler shift in the frequency will be what? How much is the light which has been scattered minus how much light which was incidented earlier. So, that is the Doppler shift. Okay. Now, if you do that, f s, the way we have calculated is nothing but c upon lambda I into, this is c minus v dot j upon c minus v dot I. Okay. You see that is the way, sorry, this is I and j, opposite way around. So, this is I and this is j. So, this will be I and this will be j, this will be j. So, V I and j, okay, and this will be minus f I is equal to c upon lambda I. So, we can take c upon lambda I out, and what you will get? You will get c minus v dot I minus c plus v dot j upon c minus v dot j. Okay. This you will get, this c will be cancelled out, and you can write it as a c upon lambda I is equal to v dot j minus v dot I upon c minus v dot j. Okay. So, we will get this value, and that is what is the Doppler shift in the frequency. Okay. So, this will be the Doppler shift in the frequency you will get, and that Doppler shift in the frequency, if you will see, is directly the function of velocity. So, this is directly the function of velocity. Okay. So, we can calculate, if I can measure the Doppler shift, I can measure the velocity of the fluid, okay, and that is the basic principle is being used. So, what we do? We incident a light, we seed it with some particles. Now, these particles are moving with the velocity of the fluid. Now, this particle is going to scatter the light. What we need to do? We need to measure the incident of the light without the presence of the particle. We need to measure the light, the frequency of the light or intensity of the light in the presence of the Doppler shift or in the presence of the particle or in the presence of the light scatter. The difference between these two, the incident and the scatter, is going to give me the Doppler shift frequency, and once you have a Doppler shift frequency, you can directly correlate it with the velocity. Okay. So, in that way you can do. Now, if I assume, and for most of the flow it's always correct, and particularly for the case of a light, this is definitely correct, that all this v is very small than the speed of light. Okay. So, say b mod of v I am taking is very less than the speed of light, and that is true for most of the application we are going to discuss, not most, for all the application, particularly if we are using laser, and that is the another reason that why we are using the laser. Okay. So, if this is true, then what we can do? We can say that C minus V is going to be equal to C. This value C minus V dot J is going to be equal to C, because the light value velocity is very high compared to V. You subtract a very small value, the value remains same. So, this will be equal to C. Okay. So, then this will be equal to C, this C and this C will be cancelled out. It means this I can remove it with C only. Okay. This I can remove with the C only. This and this C will be cancelled out, this is lambda I. So, whatever you are going to get, you will get that F d is equal to C upon lambda I into V dot J minus V dot I, unit velocities. Okay. So, this is the directional component, and you can find it out that how the Doppler shift is dependent upon the velocity. Now, if you fix a light intensity or source of the laser, okay, your lambda I is fixed, C value is fixed. So, finally, if you somehow measure the F d, you can easily measure that what is the velocity. Okay, and this you can write it simply F d is equal to C upon lambda I, this will be V j minus I, unit vector. Okay. So, that is the way it will be there, and you can find the velocity in the direction of the scattered, velocity in the direction of the incident, and you will get it that what will be the overall velocity. So, that is the principle, basic principle of measurement of the laser Doppler anemometry. Okay. So, what is the basic principle? What we will again discuss, that in LDA, effect of the Doppler shift is being used, or Doppler shift effect is being used to measure the velocity of the fluid. The flow, what we do is we seed the flow with a small tracer particles. That tracer particles actually moves with the velocity of the fluid. We keep the tracer particle specification such that it can easily represent the velocity, or it can easily mark the flow of the fluid by keeping the particle size very small, by keeping the Stokes number very less, and by keeping the particle neutrally buoyant. So, if you do all this, you can follow, or you can assume that your particles are actually following the path of the fluid, which velocity you want to map. You can use that, you can seed the particles with this tracer particle, that tracer particle will be moving inside. You form a narrow beam of the laser which has been focused on an object or on a measurement volume, you make that. So, what you do, you take this laser light, okay, you take a mirror something like this, you split that light in two, okay, or you use a beam splitters. You take a mirror, you incident it, you take a let us say beam splitter, this is the beam splitter, you break it in two beams or you split it into the two beams. You take a lens, you focus these two beams at a particular location inside the flow of interest. Okay, this is inside the flow of interest. Now, what you do, you measure this response by using a lens again, you measure this response, okay, on the receiver. Now, this receiver is nothing but a photomultiplier tube. So, this is called PMT, that is nothing but photomultiplier tube. Okay. So, you receive that signal. Now, how much shift, if you seed it with the particle, as I said, this particle will be moving. If you seed it with some particle, this particle will be moving, and once they will come here, they will shift the frequency of this incident range, okay, or this incident light. And that shift in the frequency, you can measure the Doppler effect and you can calculate the velocity. So, what you need? We are using the Doppler effect to calculate the velocity. We need the seed particles which are small enough to track the motion of the fluid phase, whose velocity we want to map. We incident a narrow beam of the light on the area of interest or an object, which I said we can say on an area of interest, and if that object is moving, say on which you have incidented, if that object itself is moving, or the particle which you are seeded, once they will pass through that measuring volume or the area of interest, what will happen? The frequency of the signal received will differ from the transmitted signal. So, whatever the frequency we have transmitted will be different from the without having the particle in the source. So, there will be, you will see the difference in the frequency, okay, or different in the signal. Now, that scattering which will take place because of the presence of the particle can be detected by a photomultiplier tube, which is an instrument that generates a current in proportion to adsorbed photon energy and then amplify that current. So, we sent it through a photomultiplier tube, and the photomultiplier tube, there is an electronic circuit inside where there is amplifier is also there. What it does, actually the moment gamma or kind of any photon incident on this or any light source incident on this, it goes to excited state. That excited state, once it comes back, it emits a photoelectron. That photoelectron goes to photocathode. It generates the electron. That electron passes through the several diodes placed inside to intensify the current signal and generate a current. So, the amount of current generated is equivalent to the energy of the adsorbed photons. Okay. So, if the photons adsorbed is of higher energy, the current generated will be also higher. So, in that way it is being proportional to this, the light is scattered, and that you can measure, and the amount of the scattered light actually you can calculate. Now, once you have the amount of the scattered light, we know that the frequency of the scattered light in case of a moving object is directly amount to the velocity or speed of the object. Okay. So, you can calculate the speed. So, that is the very basic principle whatever we have discussed till now is for the LDA velocity measurement. Okay. So, what you want? You want to measure the Doppler shift in the frequency. It means you want to measure that FD, whatever we were talking about earlier. Okay. So, FD depends on the speed of the object or speed of the seeding particle, which velocity you want to track. It also depends on the direction of the particle motion, that which direction the particle is moving, because once it will move towards the source or towards the receiver, then what will happen? If it is moving in the direction of the incident of the light, it will be negative, the Doppler shift will be less. If you are moving opposite way, Doppler shift will be high or the intensity will be higher. So, in that way it depends on the direction, it also going to depend on the wavelength of the light. So, therefore, for the LDA you need to choose a proper light, a proper wavelength of the light to improve the signal to noise ratio, and the orientation of the observer, that at what direction you have oriented the observer, and we will discuss that. Depending upon the direction of the detector or the observer, we can classify different type of LDA. So, that is going to depend on that. The orientation of observer is defined by an angle alpha between the incident light and the photomultiplier tube. We will discuss it, what it is saying. The direction of particle motion is defined by the beta angle and this beta angle between the velocity vector and the bisector of ABC. So, suppose if there is a light, I have this figure here, suppose there is a light which is being incidented. So, this is the light which is being incidented on a moving object. This object is say itself is moving, at a velocity v. So, this object is moving in this direction with a velocity v. Okay. And there is a photo detectors which has been placed somewhere at this line. Okay. So, what will happen? Once the wave will be incidented, once there is no particle, there will be certain intensity which you will record on this photo detector. Now, once the particle will be there, because of the particle velocity, this kind of light incidented on this object will be scattered. So, now what you are going to see, earlier you were seeing the f, this now you are going to see that f plus fd. So, you are going to see that what is the frequency plus whatever is the Doppler effect frequency is there. So, that what you will see that as a scattered light frequency. Okay. And let us assume if this is the alpha, where alpha is the angle between A, B and C, it means the angle between the incident light and the photodetector. If the beta is angle between the line which bisect this ABC. So, suppose this is ABC, the line which is bisect this, which is the given by this thing, this is the V, and if this is the velocity, that is the V he has taken. Okay, that is the angle, sorry, beta, this is the velocity vector, and this is the angle alpha, okay, which is the angle between the incident light and photodetector, this line ABC, that is the angle alpha. If you take a angle between the line which bisect the ABC, okay, with the velocity V, that is beta. Okay. So, in that case, if you do the trigonometry, and if there is any problem we can discuss, that if you do some trigonometry, you will get that f d is nothing but this will be equal to 2 into V x upon lambda into cos beta into sin alpha by 2. Okay. So, you can do some this calculation and you will able to calculate it, that why it comes to sin alpha by 2 and cos beta. So, what we have done, we have taken the angle in this effect. So, this will be V cos beta, and then this will be sin theta, because in this direction we want to say this will be in the direction of sin. So, this is alpha, this is 90. So, this will be going to be 90 plus alpha. So, that will be cos 90 plus alpha, that will be equal to sin alpha by 2. Okay. So, if you divide it by 2, because we need to take this much. So, we need to take this angle. So, that is what is the alpha by 2. Okay. So, what we want to measure the FD, okay, and we want to measure the FI. Okay. So, FD we want to measure ideally. Now, FD can be measured by measuring the FI and measuring the FS. If we know that FS, what is the scattered frequency, what is the incident frequency, we can calculate that what is the FD. Okay. And that is the whole principle of measurement. Okay. Now, the problem in this case is that if you have a single source and single light, okay, the single light, we face several problem, okay, and we will discuss that what is that problem. So, what we are doing, we are having a single light which is being incidented on a moving object, and we say that if the moving object with the velocity v, and it makes the alpha angle between the moving incident object, whatever it is moving here, to the photodetector, where the photodetector observer is placed, that is the alpha. Now, if the velocity is moving at a v, we define an angle beta, which is nothing but the bisector of the angle of ABC. It means the light incident on the observer to the photodetector, that is the angle. So, that is the beta, and this is alpha, then FD is given as 2 Vx upon lambda cos beta into alpha by 2. So, in that way you can give this. Okay. Now, you can divide, as I said that this is for the single light, you can divide your LDA in the two parts. One is the single beam LDA and then the dual beam LDA. Okay. Now, what is single beam LDA? Single beam LDA is where you use the single beam to measure the velocity. Now, this technique has its own advantage and disadvantage, this whole type, both type of the single and dual, and we will discuss that. So, what is the single? In this you use a single light source or single beam. So, what you do? You have a light source, okay, say this is a light source, and that light source you actually make fall. So, this is the light source, you use the lens and you focus this light source on certain location. Okay. You are focusing this light source on the second location, and then by using this lens, it is again going back to the detector. this is my measurement volume, and it is going back to the detector. Okay. Now, what we do? We need to measure what? We need to measure that how much is the frequency was there incidented, that we can measure. How much is the frequency which was recorded before the scattering, that we need to measure. So, we need what? We need to measure the reference frequency. Okay. So, that which is being there without having any flow or without having the particle inside, that is the frequency which we need to measure. So, for that what we do? We actually use one mirror which will be actually reflecting the light, and we use this mirror in some angle alpha or some angle. Now, this mirror what it does, suppose this is the mirror, I will make the mirror at certain location. So, this will be the light which will be coming, I make the mirror somewhere here or somewhere here little bit, and then that mirror is actually incidenting the light somewhere here. Okay. So, what will happen? You will get that scattered light mixed with the light which is being now kind of incidenting earlier. So, that the difference, if you do that difference, you will get that FD value. So, you will get directly that what is your FD. Okay. So, that will be the difference. So, I took a laser light, I put a beam splitter, break it in two beams, I will focus them with by using a lens at a particular location where we want to measure the velocity. We seeded the flow with the particle. Once the particle reaches there, it will scatter some of the light, that will be catched by the lens or receiver lens and being thrown to the photomultiplier tube or detector. Now, at the same time, we also measure that what will be the frequency of the light which has been incidented or on the receiver. Okay. So, without having any particle inside. So, what we do? We put a mirror, we record that frequency, whatever is being scattered, this or whatever is being transferred in all the direction, and then we focus it back to the detector or to the PMT, and before going to the PMT, these two waves are mixed. Okay. So, what you get? You get the FD value. Now, once you have the FD value, we have already developed the formula for calculating the velocity, and that formula is actually nothing but FD is equal to 2 V upon lambda into cos beta into sin alpha by 2. So, you can measure the velocity. Okay, clear? You know the beta now, you know the alpha now, you can calculate it. Okay. So, you know all these things, you know the beta, you know the alpha, you can calculate that what will be the velocity. Now, there is certain drawback. This looks very simple, that you use a light, you split it in two parts and then you kind of put it in the receiver and you record that. But there are certain drawback, and the drawback is that the Doppler shift is very small fraction of the incident frequency. Okay. So, what we are going to measure here is the FD, and that is the very small fraction or very small frequency of the incident lights, very small fraction. Okay. So, this result in estimating a very small value from the difference of two large values. So, what we are measuring? We are measuring the Fi, what is the incident, then we are measuring the Fs, whatever is the scattered. Okay. And from difference of this Fs minus Fi, we are calculating the Fd. So, what we are trying to do? Fd value is definitely going to be very small, but the value of Fi is going to be very high, Fs value is also considerably high. So, you are getting the Fd by subtracting the two large values or two very big values. Okay. So, what it will do? It will make the result of this problem is uncertain. Okay. Why? Because there can be inaccuracy generated because of the way it has been calculated, and the process generate a high degree of uncertainty in your velocity measurement. Okay. Therefore, to improve the velocity measurement further, what we do? We incident the beam, instead of one, we use the two beams. Okay. So, therefore, we use two incident beam method to improve this condition in the velocity measurement or to remove this uncertainty in the velocity measurement. Okay. So, the dual beam LDA is being developed. So, I hope it is clear that why we are developing the two beam, because what is going to happen? We are going to calculate the FD by subtracting the Fs, which is scattered frequency, minus Fi, which is the incident frequency. Okay. And to do that, what we have done? We have already mixed the two phase to this frequency at this place before it goes to the PMT. So, you have to measure that. Now, if suppose what you will happen, you will generate some error. Now, why you will generate some error? Because you are calculating the FD Doppler shift from the two values which are very high, this kind of incident light frequency minus the scattered light frequency. So, you are calculating from there. So, what will happen? The sensitivity or the accuracy of this FD measurement will not be that much good, and therefore, what you will see a high degree of uncertainty in your measurements. Therefore, to overcome this, what we do? We incident the two beams. Now, what happens if you incident the two beams? In dual beam, one single laser beam is splitted into two by using the beam splitter. So, what we are going to do? We are going to use a beam splitter to split the beam in two parts. So, suppose this is the laser, okay. We use a mirror, we use a beam splitter. So, this is the beam splitter. Now, beam split will split the beam into beam splitter, okay. Now, what we do? We use a mirror, okay. Once you use a mirror, what will happen? This some light will go on this side, some light will come on this side, okay. Now, these lights which are going here will be actually again fall on a lens, and that lens will actually make it converge. That lens will make it converge. It will again go to a lens, and then it will fall to the PMT. So, this is say PMT, okay. So, this will again fall and go on the PMT. This is the area of measurement in which we want to do. There the flow is going on it in this direction, and this is the area of maintenance or area of measurement, sorry. Now, this light whatever is there, this is the mirror which you have used, say mirror M1. Now, again one mirror is being used, and this light also incident at the same location, okay. This light is also incidented on the same location. So, this and this is the direction, okay. So, this light will be incidenting on this. So, what we do? We take a single laser in the dual beam also, we split the single laser in two different lasers, okay, by using a beam splitter and the mirror combination, okay. Now, both the beams are focused at the same location, and that location is the measurement volume or the point of interest where we want to measure the volume, okay. The other particle, the particle which will be scattered. Now, if suppose we put the particle here, we dump it with the particle, what will happen? The particle will do the scattering of both the lights. The particle will scatter on both the lights, okay. Now, the scatter which falls on the PMT along with the reference will be different for both the beams. Why? Because the particle is going to make two different angles from both the beams, and therefore, the scatter which is being the beam which is partially scattered by the fluid is going to fall on the PMT along with the reference cell, and that will be different for different beams. Why? Because the incident angle is different, okay. So, that is the basic principle is being used for the dual beam LDA, and that is the major advantage also. So, what happened that if you are using this, what will be happening? So, this is my incident light, okay. A receiver is placed, a photomultiplier tube is placed in the same direction, okay. Now, this is suppose it has been placed here in this way. Now, second light which will be coming here on this side will be incidenting at the same place. So, this is the place where it is incidenting. Now, suppose this is the place where it is incidenting, this is the velocity which is moving up, okay. So, what will happen? You will form an angle from this incident beam to the photodetector, that is say alpha 2. You will find one angle is alpha 1, okay. Alpha 1 will be, and if the theta is the incident angle, then what will happen? Alpha 1 will be equal to minus theta by 2, because this is below this 0 line. Alpha 2 will be equal to plus theta by 2, because it is above than the 0 line, okay. And then we are defining the angle beta, and the angle beta is nothing but the angle between the velocity vector to the bisect line, okay. So, suppose this is the intersect or bisect line, then this will be the bisect, and the beta will be the angle between these two, okay. So, this will be the beta 1 and this will be the beta 2. Now, if you do the trigonometry a little bit, you will find that beta 1 is nothing but this is equal to minus theta by 4, this is nothing but equal to minus theta by 4, and this is nothing but is equal to theta by 4. Okay. So, that is the way this has been defined. Now, if I write that how much is the Doppler shift you will get, what you will do, you will see measure both the intensity, okay. You will mix them, you will measure both the intensity on the photomultiplier tube. Okay. So, what you will see, now we are seeing the two Doppler shift. One Doppler shift is in this FD1, say this is FD1, you will see here. One Doppler shift you will see in the FD2. So, that will be FD2. Okay. So, FD1 minus FD2 you will get these two, and you will measure these two Doppler shift, difference between these two Doppler shift, and that difference in these two Doppler shift will result in terms of the velocity. So, what you have done, instead of measuring two quantities which are very big, say incident frequency and scattered frequency, now you are measuring the Doppler shift for beam 1, Doppler shift for beam 2, you are subtracting them to find it out effective Doppler shift on this, and that will be correlated with the velocity of the observer or velocity of the particle. So, what we are going to do? We are going to calculate FD1 minus FD2, and that FD1 by FD2 is what is, if you will see that FD2 will be nothing but it will be equal to, because the incident frequency is same, FD2 will be nothing but equal to minus FD1. Okay. So, in that case you can say that if you want to find the overall shift in the Doppler, that will be nothing but this will be divided by the 2. Okay. You got my point? Why? Because FD2 will be equal to minus FD1, the incident beam frequency is same. Okay. So, what is going to happen? Only the direction is different, but it is going to have the equal magnitude. So, FD0 is going to be the FD1. Similarly, like for this will be F plus FD2, here it will be F plus FD1. Okay. And we are now measuring that how much relative change is there. So, that will be FD1 minus FD2, and this will be divided by 2 because this is effective. So, FD1 will be equal to actually minus FD2, or FD2 is equal to FD minus 1. We can replace it, it will get 2 FD. So, that will be the overall this volume. So, this will be equal to, as we have discussed, 2 V upon lambda. Now, what is the angle in this case? So, earlier this was the one angle, and we say that is the cos beta into sin alpha by 2. Okay. So, now what will be the alpha angle? Alpha angle is, it is given theta 1 by 4. So, this will be 2 V upon lambda, this will be cos, beta is theta by 4, that will be theta by 4, this will be sin theta by 4. Now, if we are talking about beam 1 or beam 2, it can be plus or minus. So, even that does not going to change your result, because cos minus theta is equal to cos theta, sin minus theta is equal to sin theta. So, you are going to get this value upon 2. Okay. So, if you solve this, what you will get? You will get 2 V upon lambda into sin theta by 2. This is cos theta into sin theta, 2 cos theta into sin theta is equal to sin theta 2 theta. Okay. So, that is what we have used, and you will get the FD value. So, it means what? If you know the V, if you know the FD, okay, for the dual beam, if you know the incident light, if you know the frequency or wavelength of the incident light, you can calculate the velocity, okay, by the dual beam. You can calculate the same for the single beam, but the single beam, the problem, as I discussed, the problem is that you will see that you will get the FD value by subtracting two large values. So, your uncertainty will be very high, your accuracy will be compromised. Here you are getting the FD values by two small values, okay, F plus FD and F plus FD1 by this way. So, your whole sensitivity is there. Now, you are calculating that if you subtract this, you will get the FD2 minus FD1 or FD1 minus FD2. Now, we know that how much scatter will be there, that will just depend on the direction. So, direction will be opposite, and that is why FD2 will be equal to minus FD1, we will calculate the FD. So, this gives you the higher sensitivity, the better accuracy in case of the dual beam is being observed compared to the single beam. The formula remains same. So, you use these values to calculate that what is the FD value here. Okay. Now, we will discuss this part I think later on, that how to calculate this, how to do the signal post processing in the next class, but the basic principle of the LDA, whatever I said, is remains same. You measure the Doppler shift in the frequency, and that Doppler shift in the frequency is going to be the same or is going to be proportional to the velocity of the fluid or velocity of the particle which is seated in the fluid, and that velocity of the particle is equal to the velocity of the fluid. So, you can measure the velocity of the fluid. Okay, and we will discuss about the signal processing advantage and disadvantage of LDA in the next class.